All right, section 11.6. This one is a little bit longer, so it will probably take more than one video to cover, but it covers the concept of absolute convergence and the ratio and what are called the ratio and root tests. All right, so first we want to define what we mean by absolute convergence, and then we'll have two different tests to test for it. All right, so absolute convergence is a stronger type of convergence than regular convergence. So a series summation of an is absolutely convergent or converges absolutely if the series summation of absolute value in absolute value an is convergent. Okay, so to be clear, what this means is we have a series. Its terms may be positive or negative, so some of them are positive, some of them might be negative. It's not necessarily alternating, but some of the terms might be negative. If we take that series and we force every term to be positive by taking the absolute values, and we add up those absolute values, if that resulting series is convergent, then the original series is called absolutely convergent. Okay, so if it's absolutely convergent, we'll see that that means that it's also regular convergent. But we'll get to that in a minute. Let's look at some simple examples that we already understand. All right, so for example, one that we've already looked at, the summation of negative 1 to the n over n squared. Okay, so this is an alternating p series with p equals 2, and we know that if it's an alternating p series, if the exponent's bigger than 0, if it's positive, it's convergent. So we already know that this is a convergent series. All right, so that's something we've already done. But if we look at the absolute value of this, the series that we obtain if we take the absolute value, well, taking the absolute value is just going to get rid of the alternating part. So if I take the absolute value, the negative 1 to the n doesn't matter. It's forced to be positive in all cases. And so in that situation, if I do that, I get the ordinary p series, 1 over n squared. That's convergent because for positive p series, p needs to be bigger than 1 to be convergent. So this is convergent. So the fact that this is convergent tells us that the alternating one is not only convergent, it's absolutely convergent. Absolutely convergent. So as we'll see, if it's absolutely convergent, it will always be convergent. But we haven't proved that yet. Okay, so let's look at a similar example. I guess I'll just rewrite it. If we did the same thing with the alternating harmonic series, so negative 1 to the n minus 1 over n. That's a alternating p series with p equals 1. That's convergent. If I take the absolute value series, it's again going to eliminate the alternating part, and it's just going to give me 1 over n. That's divergent. The harmonic series is divergent. So what that tells me is the original series is not absolutely convergent. So this one is convergent, but not absolutely. And I guess that's when this happens, the series is convergent, but not absolutely. That's called conditionally convergent. Conditionally convergent. Where it's convergent but not absolutely, that's conditional convergence. All right. So the main point of this is what I've already said. If a series is absolutely convergent, then it's automatically convergent. So this is a theorem. I'll just say it like this: absolutely convergent implies convergent. And the proof, or the so-called proof, is by a squeeze, well, sort of like a squeeze theorem argument, or comparison theorem, I guess. If I look at an plus absolute value an, the biggest that could possibly be would be in a situation where an was already positive, this would equal 2 times the absolute value of an. Because if an was positive, they'd both be the same. I'd get 2 of the absolute value an. The smallest this could possibly be is if an's negative, an and its absolute value will have opposite signs, so they would cancel. Okay. So we have an plus its absolute value is trapped between 0 and 2 times the absolute value an. So if we assume absolute convergence, I'm abbreviating here, but if it's absolutely convergent, that tells us that this side here produces a convergent series. So that tells us that the middle part is convergent. If I add up the middle sequence, that's a convergent series. Well, then I can subtract absolute value of an, that series. I got distracted by a cat there. Come here. We can then conclude that if this middle part's convergent, if this middle part converges, start again. If this middle part produces a convergent series, and the absolute value part by itself produces a convergent series, then that forces the other part to produce a convergent series. All right, so I don't think it's worth writing it down. This is the basis for the theorem. He's in the way again. All right, let's illustrate the purpose of this. So if something's absolutely convergent, that implies it's convergent. Okay, so it isn't that this new concept of convergence matters for its own sake. So it's not that knowing that a specific series is absolutely convergent tells us anything special about that series. It's just another avenue for showing that a series is convergent. Because, like we saw earlier, with the comparison tests, those are only applicable when we have positive term series. When our series consists only of positive terms. So, for example, if I was going to look at the series sine of n over 3 to the n, as n goes from 0 to infinity, this is a complicated series. Sine of n is not always positive, it's not always negative, it's not alternating. I mean, it sometimes it's positive, sometimes it's negative, but it's not strictly alternating back and forth. So I can't use the alternating series test for this, and up to this point, other than the alternating series situation, all of our tests, comparison tests, integral test, those required positive value series, positive term series. So what I would do is, let's take the absolute value of this. Now it's positive. I can say, what's the largest the sine of n could be, the absolute value of sine of n could be? Well, it has to be less than or equal to 1. So this is less than or equal to 1 over 3 to the n. It's obviously greater than or equal to 0. So this is a positive series, positive sequence. Stop. It's less than or equal a geometric sequence, and this geometric sequence would give me a convergent geometric series. So summation of 1 over 3 to the n, that converges. That tells me that if I add up these absolute values, what are you doing? That series converges. All right. So the fact that this absolute value series converges, that tells me by the definition that my original series is absolutely convergent. Let me abbreviate. And I don't need to specify, I don't need to say it specifically, but now that I know this converges absolutely, it therefore also has to be convergent. So now I know that this is a convergent series because its absolute value series converges. Okay, so basically, I kind of mentioned this last time with the alternating series test. It's easier for an alternating series to converge than it is for the non-alternating series to converge. So basically, by making every term positive, by taking the absolute value, that's kind of a worst case scenario for whether or not a series is going to converge or not. So if it converges in that worst case scenario, then it converges in the simpler case where not everything's positive. When terms are not always positive, there's cancellation when I'm adding them together, because some are plus, some are minus, so there's some cancellation. So it's less likely to be infinite in that situation than if I force everything to be positive. Okay, so that's the idea. So sometimes you can directly, by taking absolute value, we can then use a comparison or a limit comparison, or I guess hypothetically we could do an integral test in some situations. But the main tests that we use in these kinds of situations are much more direct. So let's talk about the first of the two, the ratio test. The ratio test. All right, so we've got a series, summation of an, and we look at a certain limit. So suppose the limit of, I'm going to take absolute values, because this is a test that involves absolute convergence, so there's absolute values involved. But what we take the limit of is a ratio, so hence the name ratio test. What it is we take the term an and we do a ratio. The an plus 1 term, and we divide that by an term. And take the limit as this ratio, we take the limit of this ratio as n approaches infinity, and suppose it equals L. And here L could be infinite. So I'm including infinity as a possible value for my limit. Okay, so then I compute this limit, and then I look at my answer, and depending on what that answer is, determines what the outcome of my ratio test is. So there's 3 cases. The first case is if L is less than 1, then our series, summation an, is absolutely convergent. And therefore also convergent by the previous fact. So my limit comes out to be a small number, less than 1. That includes 0, so it could be 0. It'll never be negative, though, because we're taking a limit of a positive sequence because of the absolute values. But if this answer comes out to be a small number, less than 1, then we have absolute convergence. If it comes out to be a large number, so if L is greater than 1, we get divergent. So the original series is divergent if that happens. And the third case is if L equals 1 exactly. So if L equals 1, in that case, we get inconclusive. Okay. And if it's inconclusive, then I'd have to use some different method to try to answer the question for the given series. All right, so let's do an example. You'll want to have this in front of you. I'll have to erase it. All right, so let's consider an example. Summation of -1 to the n plus first times n squared over 4 to the n. From n equals 1 to infinity, maybe. All right, so probably in a problem over these, I would tell you for this problem, use the ratio test or use the root test. Will be the next test after this. Or I'll make you decide between the two, but I'll at least narrow it down to one of the two. I'll narrow it down to this section. We could potentially use an alternating series test here. I'm not really sure. I have to test whether this is decreasing or not. But in this problem, we will use the ratio test. So what I do is this whole thing, that's an. So I want to look at the limit as n approaches infinity of the absolute value of an plus 1 over an. Now, first thing is, an in this case involves a -1 to a power. Taking the absolute value is just going to make it all positive, so I can basically ignore the -1 to the power. So I'm not gonna bother writing the negative 1 to the power. I'll keep the absolute values for now. an plus 1, that's this expression. Again, I'm ignoring the minus 1 part, but it's this expression with n plus 1 plugged in. So I would have n plus 1 squared divided by 4 to the n plus 1. That'll be the top of this fraction. Then I'm dividing that by an. Again, absolute value is going to eliminate the negative 1. That'll be this expression with just n plugged in. So that's n squared over 4 to the n. Now, I don't really like dealing with these complicated fractions. So in the future, when I set these up, the way I'll do this is most of the time we're dealing with fractions, and we'll have fractions of fractions, and if we do it this way. So instead, the way I clean it up is, let's write an plus 1. So n plus 1 squared divided by 4 to the n plus 1. And then instead of dividing by an, we're going to multiply by its reciprocal. So we'll flip it. 4 to the n over n squared. Okay, so now I need to do the limit. This looks like a complicated expression, but the good news is most of the time in ratio test problems, there'll be a lot of kind of standard simplifications to make. The way to accomplish it is, an consists of two parts, the n squared part and the 4 to the n part. When I set up my ratio here, I want to group the corresponding parts. So n plus 1 squared divided by n squared. Put those two together. Four to the n divided by 4 to the n plus 1. Put those two together because they're both the 4 part. In this case, everything's positive, so I don't need the absolute values. Okay, so let me continue, but let me erase. All right, so now these parts, well, let's do the easy part first. 4 to the n divided by 4 to the n plus 1, there's going to be cancellation there. I have one extra 4 on the bottom than I have on the top. So that'll be 1/4. So I'll have 1/4, and I've got this part. Now here, let me think of it like this. That's n plus 1 over n squared. That's a rational function. Let me erase this stuff. That's a rational function with the same degree on the top and the bottom. So its limit's just 1 over 1. The leading coefficients, 1 over 1. So this is 1/4. The limit of this is 1/4 times 1 squared, which is 1/4. So there's my answer. And remember, the successful condition is if this is less than 1, which it is, that tells us that our series is absolutely convergent. Meetsy. Okay, so again, we use the ratio test to determine convergence. As a byproduct, it gives us absolute convergence in this case. That just means whether or not I had this minus 1 to the n. So if that wasn't there, it still would have given me a successful condition. I'd get convergence. So we really care that we got a convergent outcome. All right. So let's do some more examples, and then I'll argue why this works. So let's do this one. If I had something like n squared over this too much. Sorry. Let's do summation of n over n squared plus 1 n equals 1 to infinity. So if I try to do this with the ratio test, this time everything's positive. I'll put the absolute values just for the habit, but everything's positive anyway. In the n plus 1 version of this would be n plus 1 divided by n plus 1 squared plus 1. Now I need to multiply by the reciprocal of the n version. So I'm going to flip this fraction. N squared plus 1 divided by n. Now, there's different ways I could approach this. I could multiply everything out and get a simple, I could get a single rational expression. Instead, let's go with my technique from before. There are basically two parts. There's n and there's n squared plus 1. Let's group them according to type. So, I've got n plus 1 over n and n squared plus 1 over n plus 1 squared plus 1. N plus 1 over n, that by itself is a rational expression with the same degree on the top and the bottom, n over n, so that's going to approach 1 over 1. Here, I need to multiply out a little bit, but if I multiply this denominator, I have n squared plus 2n plus 1, so plus 2. So n squared over n squared, that's the same degree. So this is going to approach 1 over 1. So that approaches 1. So this limit is 1 times 1, which is 1. And as we talked about when we introduced the ratio test, if we get exactly 1 as our answer, that's inconclusive. So the ratio test doesn't tell us the answer to this. And that's going to generally be the case. Well, not generally. That will always be the case when it's the sum of just a rational expression. So this is all just polynomials here. N divided by n squared plus 1. Or even if there's like square roots. If it's just like a rational expression or powers of n involved, the ratio test won't work. It'll be inconclusive every time if that's all that's happening in our sequence. Okay, if our formula has nothing more complex than powers of n. All right, so the right way to do this particular problem would be to go back and use a comparison test. So we could compare this to a p-series, either with a standard comparison or with a limit comparison. Okay, so ratio test doesn't help us with that. What it does help us with is when we have combinations of formulas, including exponential expressions, so like a number to the nth power, or especially factorials. Factorials are really are handled very nicely by ratio test. So let's look at one of those. Suppose we had the summation of n factorial over 8 to the n. So let's do a ratio test. There might be other ways of doing this. That's not the point. But let's do a ratio test for this. So it's already positive, so I don't really need the absolute values here, but we'll stick with them. So I want the n plus first version of this expression. That'll be n plus 1 factorial divided by 8 to the n plus 1 times the reciprocal of the nth term. So 8 to the n divided by n factorial. Now we want to simplify that. So group together similar factors, n plus 1 factorial over n factorial times 8 to the n over 8 to the n plus 1. So now remember what happens when we divide factorials. You figure out which one is bigger. N plus 1 is bigger. What does it have that n doesn't? Well, it has n plus 1. N factorial is going to cancel. N plus 1 factorial is n plus 1 times n and everything below n. That's exactly n factorial. So this becomes this n plus 1. 8 to the n divided by 8 to the n plus 1. That's 1 over 8. So now as n approaches infinity, we have n plus 1. That approaches infinity. Divided by 8. That's still infinity. So my answer is infinity. And for the purposes of the ratio test, infinity, we know infinity is bigger than 1. So that's a limit which is bigger than 1. That tells us divergent for our answer. Okay, let's do one more example, and then I'll try to explain why the ratio test works. So let's do another factorial problem. Yeah. Say n minus 1 factorial divided by 2n quantity factorial. So that's 2n, and then that entire thing, you take the factorial of it. I guess that's safe, yeah. If you start with n equals 1, that works. Because 0 factorial is 1. All right. So as I've said, and as I'll continue to say, if you're trying to figure out convergence of a series that involves factorials, the overwhelming likelihood will be use the ratio test, because ratios handle factorials very nicely, as we've seen multiple times now. So we'll do the limit as n approaches infinity. The absolute value of the n plus first term. So if I replace n by n plus 1, n plus 1 minus 1, that'll be n factorial. If I replace n by n plus 1 on the bottom, that's going to be 2 times n plus 1. That's 2n plus 2 factorial. So I replaced n with n plus 1, but then I had to distribute the 2. So that gives me 2n plus 2. 2 times n plus 1, and then I take the factorial after that. Right, so then I multiply by the reciprocal of the original term. That's 2n factorial divided by n minus 1 factorial. So now we have a lot of factorials, but I find it really helps if we group things according to where they came from. So n factorial and n minus 1 factorial, those both came from the n minus 1 factorial part. So put those two together. The 2n and the 2n plus 2 both came from 2n factorial, so group those together. And then you do the cancellation for each group. So n and n minus 1. N's bigger, so it has extra factors, one extra factor. When I cancel, I'm left with n. Here, 2n plus 2 is bigger than 2n, so it has extra factors, but now it has 2 extra factors because it has the plus 2. So I'm going to have 1 over 2n plus 2 times 2n plus 1. Let me continue up here. So that's going to be the limit of n over, if I multiply this out, that's 4n squared plus 4n plus 2n is plus 6n plus 2. So if you FOIL that out, that's what you get. Now all I really care about in determining this limit is the top is n to the first power, the bottom is n squared. If the bottom has a larger power, this limit's 0. And 0, now we're done with taking the limit. Now we need to determine what it says for the ratio test. 0 is less than 1. That tells me the series is absolutely convergent. And so we're done. Okay, so that illustrates a few examples of using the ratio test. Again, the big takeaway is ratio handles factorials very well. It also handles exponential expressions like 3 to the n or 8 to the n, like on the previous one, 8 to the n. That kind of thing is handled nicely when we get to the cancellation part. So those things are handled nicely if all that's going on is a rational expression, so a polynomial divided by a polynomial or something similar. If that's all there is, the ratio test is always going to give you an answer of 1, and so it'll be inconclusive. If there's more stuff going on, like a factorial or an exponential function like 3 to the n, then that'll contribute something other than 1 to the limit, and so it won't be inconclusive. All right, so let's briefly argue why does it work? Why does the ratio test work? Okay, so suppose, let me just do one of the cases. Suppose, or say, that the limit of an plus 1 over an equals L, and L is less than 1. So we'll do the convergent case. So this is kind of similar to our limit comparison theorem proof, or limit comparison test proof from a few sections ago. If L is strictly less than 1, I can find a number between L and 1. So I want to pick a number R which is bigger than L and less than 1. Then for large N, an plus 1 over an has to be less than R. Well, if this is true, that tells me that an plus 1 is less than R times an. So rather than getting to the gritty details of this, my actual next term, the next term in my actual sequence, an plus 1, in absolute value, the next term is less than the previous term times R. That should be reminiscent of a geometric sequence. A geometric sequence, this would equal R times the previous term. If this equaled R times the previous term for every n from now onward, it would be a geometric sequence. Geometric sequences are achieved by repeatedly multiplying by the same common ratio R. All right, so this is with some hand waving here. that tells us that our sequence is less than a geometric sequence, a certain geometric sequence, where the ratio is less than 1. R is less than 1. So, I have to renumber it. If I repeatedly do this, this turns into like R to the K times some starting number A, where K is the number of steps beyond that specific term A. I don't want to get into it, but the idea is, you can read the details in the textbook. The ratio test works because when this is true, I can compare my sequence to some geometric sequence, some convergent geometric sequence. On the other hand, if this limit was bigger than 1, I could fit R. Let me just start it off here. I could pick an R which is bigger than 1 while being less than this limit, and then I could compare my sequence an plus 1 to a divergent geometric series. I could compare my absolute value series to a divergent geometric series. Again, the details are not difficult, but kind of a pain to number things. Okay. So that's it for the ratio test. We're not done with section 11.6. There's still the root test to talk about. Let me stop the video here in a second. In the next video, we will pick up and talk about the root test, and depending on how long that takes, I will also probably talk about just kind of a summary of all of our tests so far. That gets into 11.7, which is just a summary section that puts together these tests into a general kind of thought process for how to approach an unknown series. But that's the plan. So we'll stop there.